Hi everyone, welcome back. The case studies covered in the last video was a spectrum of gold deposit types, mostly Archean orogenic gold, Red Lake, Abitibi, Hemlo. There are also, I mentioned, for example, Bruce Jack in BC, which is a Phanerozoic epithermal veins. While the fundamental STT model applies to all, there are clear differences in how each component manifests in different geological environments. So now we're going to talk about that. So on the source differences, orogenic gold deposits, Archean and otherwise, typically have metamorphic source. It means that broad area of crust undergoing prograde metamorphism release gold-bearing fluids. And these fluids are characteristically carbon dioxide rich, low salinity, and carry gold in reduced complexes such as gold hydrogen sulfide. The source region are deep, mesozonal to hypozonal, between 5 and 20 kilometers at depth. And they're large in scale, which is why orogenic belts produce many large deposits. In contrast, epithermal deposits like Bruce Jack have a magmatic source, specific igneous intrusion or clusters of intrusion at shallow depths, to say less than 5 kilometers, that exhaust a limited volume of magmatic fluids. Those fluids are often saline or at least water-rich and can carry gold in colorine complexes if oxidized. Intrusion-related gold, these systems, like what we talked about some Abitibi's cases or other Phanerozoic systems, straddle these categories. They may involve magmatic fluids, but often still require metamorphic country rocks to provide enough gold, or a combination of both. That we talked that is a topic of ongoing research. Also, source in epithermal context can involve meteoric water mixing, whereas in orogenic systems, meteoric water plays little role at the source. And the difference in transport, in orogenic gold, transport is dominated by deep, high-pressure fault or channel flow. The fluids travel long distances, up to several kilometers vertically, sometimes laterally along the structure for tens of kilometers. And they travel along major shear zones. Transport durations might be prolonged, for example, millions of years of episodic flow during an orogeny, and occur at between 250 to 400 degrees C. In epithermal systems, transport, on the other hand, is short-lived and shallow. Fluids rise perhaps 1 to 2 kilometers from an intrusion into the near surface. The temperature is between 150 to tops 300 degrees C, and often at much lower confining pressures. Therefore, epithermal fluids typically boil during transport, which effectively blurs transport and trap. Transport is transport is cut short by self-sealing when boiling occurs. The structural conduits differ in scale. Orogenic system requires big regional faults for upward fluids, whereas epithermal systems exploit local faults, fractures above an intrusion, often related to volcanic tectonic structures. One could say orogenic transport is plumbing of the crust, while epithermal transport is plumbing of a volcanic edifice. Chemically, both rely on gold complexes, but epithermal fluids might lose golden rod if they boil too early or react with calcite in the shallow environment. Whereas orogenic fluids can travel farther before precipitate and drop golds, often waiting for a structural trigger. Hemlow's case of melt transport is unique. I would like to say that, but underscores that in high-grade metamorphism, transport can occur in the dark-tide regime, which doesn't happen in the shallow epithermal setting. Okay, talking about trap differences, we already mentioned that we can have a structural trap, chemical traps. Structural traps are actually important in both types, in orogenic gold deposit, epithermal gold deposit, but at different scales and size. Orogenic deposits often occur at compressional structural sites, such as fault hinges, transpressional fault bands, duplex structures, and this reflects their formation during regional compression, often synorogenic. The resulting veins can be strongly foliated or laminated. In contrast, in epithermal traps, they are typically extensional veins in dilational jogs of normal strike slip faults in a volcanic setting, sometimes related to caldera structures or resurgent damming. For example, Bruce Jack veins likely formed during an extensional transtensional event in an arc. Chemical traps also differ. Orogenic gold commonly involved sulfidation of iron-rich host rocks, banded iron formation, ultramafic basalts. This explains why many orogenic deposits are in or adjacent to iron-rich units. We saw this at Hemlow, the arsenopyrite replacing iron-rich schists. On the other hand, epithermal deposits rely more on boiling and oxidation as traps. And the host rock composition is less critical, except for local effects like what we talked about in Bruce Jack, where mafic hosts did cause some sulfidation too. But the main trigger is boiling. Talking about the temperature, pressure drops, there are universal triggers. Falling temperature and pressure will cause gold precipitation in any hydrothermal systems, but in epithermal systems, these drops are abrupt, boiling, mixing with cold water, whereas in orogenic systems, pressure drops are often episodic. Seismic pumping, we talked about that already. And temperature drops are gradual in orogenic systems as fluid moves upward or into the cooler host rocks. On the scale and continuity, if we want to compare these, the orogenic system often form extensive vein networks that can be continuous over kilometers vertically. They can be very high grade in pockets, but also have lower grades. Halo you can find for the orogenic golds. Epithermal systems are usually more restricted in vertical extent, maybe 500 meter vertical. Orogenic traps may allow repeated replenishment, multiple events over a long deformation period, while epithermal traps are often one and done. Once the system seals, the effect is largely over. It's geologically rapid. So the STT model provides a unifying network. A source that generates the gold-bearing fluids, transport that brings that fluids to a depositional site, and traps that accumulate the gold. The specific vary here is metamorphic versus magmatic source, deep crustal faults versus shallow fissure transport, and structural bend versus boiling as traps. So for source transport traps, we have these differences. Understanding these differences is crucial for exploration. Talking about the orogenic belt, one might seek structural intersections in green schist trains where metamorphic fluids focus, whereas in epithermal exploration, one might seek evidence of hollow surface boiling, for example, breccias above the intrusions. So despite the differences, a common theme emerge. The largest gold deposit often requires an optimal interplay of all three STT factors. As a general rule, actually that is borrowed from petroleum geology, the biggest deposit form when the source is large, the transport mechanism is efficient, and the trap is active and ready at the right time. Each of our examples showed this. Red Lake had an exceptionally large source and efficient trapping. Brucejack had an extremely effective traps by boiling and a powerful source, magmatic fluids, to create a high-grade gold, and so on. So the source transport trap model is a powerful conceptual tool to dissect the formation of gold deposits by examining each component, source, transport, source as the origin of golden fluids, transport as the pathways and processes moving gold-bearing fluids, and trap as the condition that precipitates and concentrate gold. We can gain structural understanding of why deposits form and where it did. So what we did is that we applied STT model to a range of Canadian gold deposits from Archean gold camps to Jurassic epithermal vein system. You can see in this table. This analysis demonstrated the versatility of the STT framework in Archean orogenic belt like Red Belt, Abitibi. The source was regional metamorphism of greenstone sequence. Transport was via crustal scale shear zones, and traps were created by structural dilation and rock chemistry. In the Hemlo deposit, we saw a special case where metamorphism itself remobilized and retrapped gold, highlighting that STT process can reoccur in multiple stages. In magmatic epithermal systems like Brucejack, the source is magmatic intrusion, transport is rapid sense in fractures with magmatic fluids, and the trap is largely fluids boiling and mixing in the shallow crust. For both industry and academia, thinking in terms of the STT helps to predict where undiscovered gold might be. For example, if one can identify a potential source area, say a particular stratigraphic unit or intrusion known to generate gold-rich fluids, we can then look for connected structures that could transport those fluids along those structures, and then search for likely trapping site, bends, lithological contacts. So the case studies that we talked about reinforce this logic. Exploration successes often come from recognizing a piece of puzzle, for example, woodinized iron formation, and then fitting it into the STT complex can help to improve the exploration strategies. The STT model underscores the continuum between different deposit types. Even though we classify deposits as orogenic, intrusion-related, epithermal, etc., the fundamentals of ore formation, a metal source, a means of transport, and deposition mechanism are universal. Modern research that we cited a lot of them here challenges aspects of this model. For example, discussion on whether intrusion-related and orogenic gold deposits are separate or part of the spectrum, and whether the classic source transport trap paradigm needs expansion for complex mineral systems. Anyway, the STT paradigm, I think, remains a useful model for understanding mineral systems. It provides a clear, compartmentalized way to evaluate what we know and what we don't know about any given deposits. Have we identified the source? Do we understand the plumbing and transport? What was the actual trap for gold? These are the questions that we can answer with the STT model. So in conclusion, applying the source transport trap model to gold deposits revealed the commonalities and nuisance of how nature concentrates these precious metals. By comparing diverse examples, we see that rich gold ores results from convergence of the right source, right conduits, and right trap. And this integrated perspective is valuable for both developing genetic theories and guiding exploration strategies. As a famous phrase in economic geology, it says, ore deposits form where the 5 rights intersects: the right rock, right time, right place, right process, and right preservation. The STT model helps ensure at least 3 of these rights: source, transport, and trap, in our quest to understand and find the next gold deposits. Thank you all for watching, and stay tuned for my next set of videos for gold.